So we talked about the conservation of momentum before. Now let's talk about it in a little bit more detail. So what is conservation of momentum? Momentum is a conserved quantity, and what that means is that the total momentum of any closed system, and a closed system is the one that's not affected by external forces, cannot change. For a closed system, the total momentum of any group of objects remain the same unless an outside force acts on the object, and that is called the law of conservation of momentum. So a little bit of distinction here that I want to mention. Closed system, it means a system in which no mass enters or leaves the system, and an isolated system means no external net force acts on it. So watch this animation very carefully. Also, while you're watching this animation, note what happens to these three numbers. So we initially have a cart, which is 100 kilograms, and we have a drop brake that is 2 kilograms. Sorry, mass of the cart is 1 kilogram, and mass of the brake is 2 kilograms. And initially, the dropped brake is at rest. Even though it is moving in a horizontal direction, we still consider that the motion is not, it's giving me a zero velocity in the x direction. So only the cart has the initial velocity of 60 centimeters per second. So the total momentum of the cart is initially 60 kilograms centimeters per second. And for the drop brake, initially the velocity is 0 as well as the momentum is 0. So what you're going to notice here is when both of the objects become one object, what you're going to use is before the collision, the cart was at 60 and the brake was at 0. And after the collision, the cart has actually lost the velocity and the brake has gained the velocity, but the total momentum is conserved. It was 60 before the collision, and it is also 60 after the collision. Note, this only happens for a closed system. Right, so the momentum lost by the cart is actually gained by the drop brake, so the total momentum of the system is conserved. So conservation of momentum, I want to ask you a question, and I'm not going to give you the answer to that. You should be able to figure this out yourself. So if you have a mass m1 going with a velocity v1 and a mass m2 going with a velocity v2, they are coming towards one another and they are colliding with one another and they go away after the collision. What happens? Now that you've had time to think about it, let's talk through what the problem was. So during the interaction, for my mass m1, if I take my coordinate axis to be x and y this way, for my mass m1, the weight of the object was downwards, the normal force that's acting on this object is upwards, and there is a force exerted on this mass during the interaction by mass 2. For mass 2, the normal force was N2, the weight was acting downwards, and the resulting force was F12 that was acting on it. And if you were to write the force equations on both of them, these are the two force equations that you'll get around the x-axis and around the y-axis. Note that Fx is the only force that acts on it, and so the acceleration is only happening in the x direction. Same thing for the second mass, only acceleration happens in m2. The net force here, normal force is equals to weight 1, and normal force 2 equals to weight 2. So the forces F1 and F2 are internal forces. This means that delta P1 should equals minus delta P2. That means F1 and final for momentum for the first one minus the initial momentum for the mass 1 equals final momentum for F2 minus initial momentum for F3. So a little bit of rearranging, you can have that the total initial momentum, which is P1 plus P2, equals P1 plus P2 final. In other words, initial momentum equals final momentum. That means the momentum is conserved. And this statement is valid only during the interaction. So let's do a problem. A rifle has a mass of 4.5 kilogram and it fires a bullet of 10 grams at a muzzle speed of 820 meters per second. What is the recoil speed of the rifle as the bullet leaves the barrel? So in this example, It says the rifle mass of the rifle is equals to 4.5 kilograms. And it says the mass of the bullet is 10 grams. So see, it's grams. What do we have to do for grams? We have to convert it to kilograms. So 1,000 grams is 1 kilogram, which basically means that 0.001 kilograms is what I'm going to get. Actually, is that true? This is 10 divided by 1,000. I think it's going to be 0.010, right? Kilograms. Then I have a velocity of the muzzle, with a muzzle velocity of 820 meters per second. And what it's asking me is for recoil, velocity of the rifle. So in this case, I can use the change in momentum. I know delta P equals 0. This means P final has to equal P initial. So what do we have? We have for initial, M of the rifle, velocity of the rifle final, plus M of the bullet, and velocity of the bullet final, equals mass of the rifle with initial rifle velocity plus mass of the bullet plus velocity of the bullet initial. So the final equals the initial velocities. Okay. Now the initial velocities for both of them are equals to 0, right? That means both of them can go away. What am I left with? The rifle velocity, rifle final, bullet velocity, bullet final velocity. Okay, so that means this is the muzzle velocity that's going to go in here. So what I'm going to get is 4.5 kilograms, which is my rifle mass here, plus mass of the bullet, which is 0.01, times the velocity of the bullet, which is 820 meters per second, equals 0. And you can do a little bit of math, and what you're going to find is that the velocity rifle is going to come out to be minus 1.82 meters per second. What does the minus sign mean here? Well, the minus sign here means is that if the bullet is going forward, the rifle is going to be coming back. And if you've ever fired a gun, you know how hard that hits you in the shoulder. Question 2. A man of mass 65 kilograms is running along a pier at a speed of 4.9 meters per second. He jumps from a pier onto a rowboat of mass 88 kilograms that is drifting without friction in the same direction at a speed of 1.2 meters per second. When the man is settled in the rowboat, what? So example 2, it says a mass of a man is 65 kilograms. And he's running along the pier with initial velocity 4.9 meters per second. And the mass of the rowboat, I'm just going to call it boat, is 88 kilograms. And it is initially going with 1.2 meters per second. And it's asking us what is the final mass, man plus boat mass. Well, looking at this, it should be obvious that we have to use the delta P equals 0, which means P initial should equal P final. Or let's turn it around so that P final equals P initial. So what is P final? P final includes the mass plus the velocity. But which mass and which velocity? Well, the mass that it's going to need is going to be the mass of the man plus the boat in both cases. Whereas initially it was the mass of the man plus the velocity of the man plus the mass of the boat times the velocity of the boat. You see, this is now going to be a system because now they're not individual anymore. They're actually sitting inside the man and the boat. Okay. So in this case, this mass is going to be 65 plus 88 times V, which we are looking for, will be equals to mass of the man was 65, its initial velocity was 4.9, plus mass of the boat was 88, and its initial velocity was 1.2. Now all you have to do is plug it into your calculator and solve. So the velocity final that I calculate is 2.77 meters per second. Okay, so this is now going to be the velocity of the man plus the boat.